Soft Robotics, A Hard Road to a Better Machine by Carrie Chun. In the murky depths of the ocean, a small white creature glides just above the ocean floor. The periodic flapping of its wings are nearly imperceptible, and yet, somehow, the alien-like fish continues to fly along the bottom of the Marianas Trench. Scientists and civilians across the globe are elated, but not because of the discovery of a new oceanic creature. Rather, the first soft robot has survived a trip to the deepest part of the ocean. Soft robotics remains one of the most groundbreaking and emerging fields of robotics and mechatronics study. While traditional electromechanical systems makes use of rigid supporting and actuation structures, soft robotics focuses on developing complex movement through the use of compliant members. Consider how the arm of an excavator functions. A series of rigid beams are connected at a finite number of joints. These beams are then articulated by actuators that apply linear forces along a single axis. The excavator represents the traditional approach to robotic systems, yielding a machine with a very predictable motion profile and a finite number of degrees of freedom. By contrast, consider the trunk of an elephant. When inactive, the elephant's trunk is soft and pliable, but just below the skin, there are hundreds of sinews and tendons that give the trunk tremendous strength and unprecedented dexterity. An excavator can rip a tree from the ground about as easily as an elephant, but the elephant can pluck the leaves from the branches in a way that the excavator could only dream of. The elephant's trunk represents the vision of soft robotics. In this rapidly developing field of research, mechanisms with nearly infinite degrees of freedom are being created from compliant or flexible materials. Actuation of these members may then be completed through the use of applied fluid pressure or internal tensile structures that often act in nonlinear ways. For all intents and purposes, soft robotics are nearly antithetical to the traditional rigid robotics that have come before. Much of the field of soft robotics is considered bio-inspired. This means that scientists and engineers look to nature for inspiration on how to create these unique mechanisms. Animals such as the elephant or octopus provide a starting point as researchers attempt to duplicate the complexity that comes so effortlessly to the natural world. For example, many species native to the Marianas Trench provided pertinent clues to how a soft robot might be created for cruising at such tremendous depths. However, soft robots are not confined to exploring the ocean. Researchers at NASA's Langley Research Center are interested in using soft actuators in further extraplanetary explorers. They hope that the organic likeness of soft robots will allow them to better adapt to complex alien terrains. Being able to adapt to change in real time is also important for terrestrial applications of soft robotic systems. The Weiss Institute, part of Harvard University, has been exploring the potential for soft robotic exosuits. Prototype systems are worn like any garment or article of clothing, but soft actuators embedded within the suit provide targeted forces that act to assist the wearer. Connor Walsh, the lead researcher for the project, emphasizes that the design of the exosuit was based on the physiology of the human leg, with actuation taking place in parallel to existing tendons and muscles. By their nature, soft robots are inherently safer to operate in close proximity to humans. It is therefore no surprise that the potential biomedical application for this emerging technology is numerous. Creating prosthetic limbs or assistive exosuits could allow amputees and paraplegics to regain significant mobility and independence. Medical instruments created from soft linkages or compliant members could also prove to be less invasive than modern rigid surgical equipment. Safer, human-friendly robots also have the potential to help humanity in a more personal way. At Carnegie Mellon University, a team of scientists led by Christopher Atkinson created an inflatable robotic arm, which later inspired the concept for the caregiving robot Baymax from Disney's Big Hero 6. While robots such as Baymax may be far from reality, soft robotic systems that can work safely with humans and for humans are still a major area for continued research. With a rapidly growing elderly demographic in the United States, consumer robots capable of doing housework or even medical caregiving could provide the quality of life and provide a safe means for elderly Americans to remain independent. However, traditional robotic systems are unlikely to find their way into an average home because the powerful actuators and rigid linkages could cause harm if they were to go astray. By contrast, a soft robot system could still maintain the precision necessary for complex tasks while posing little to no danger to an elderly individual. Research into inflatable robots continues, with companies such as Robotics, who are developing robotic actuators and arms based on the initial prototypes created by Carnegie Mellon. The robotic arms being developed by Robotics resembles arms used by industrial assembly lines. However, the inflatable arms are soft and pliable, making them completely safe to use around humans, unlike most industrial robotic systems. Other companies have shown great success with implementing compliant actuators and graspers with industrial assembly lines. Soft Robotics Incorporated has developed a number of products, with their website claiming that multiple Fortune 500 companies have invested in their systems. Through the use of compliant graspers, Soft Robotics Incorporated has created pick-and-place machines capable of delicately transferring objects as soft as marshmallows. Moreover, these devices excel at working with irregularly shaped objects, such as vegetables or other food items, making the soft graspers more effective and faster than traditional rigid devices. Specialized soft graspers may also be able to be miniaturized for use with molecular transport. Scientists associated with Northwestern University created prototype four-legged soft robots that could be controlled using a combination of light and external electromagnetic fields. When operated in water-filled environments, the octopus-like devices proved to be effective at rudimentary walking and the transportation of small spherical loads. Future renditions of this device could be further miniaturized to help catalyze chemical reactions or even for the collection of unwanted particles from fluid-filled environments. Soft robotic applications are also not confined solely to scientific endeavors. Researchers at the University of California identified hard electronics as a major stumbling block to future soft robots. Therefore, they developed one of the first modern air-powered or pneumatic logic systems. By using the presence of air pressure or a vacuum to simulate the zeros and ones in typical electronic logic circuits, the rigid electronic components of a typical robot could be replaced with flexible air tubing instead. While the process and memory capacities of the system remain very limited, the proof of concept prototype was utilized to actuate a simple piano-playing robot. However, it may be this piano-playing soft robot presents the most tantalizing vision of the future. Humans have long been fascinated with the pursuit of art, but the human race may now be on the verge of developing artificial entities capable of creating art on their own. If such devices are even possible, an artificial entity capable of creative thought, it will be the organic nature of soft robotic actuators that may be the key to allowing this artistic expression. The piano-playing robot created by the University of California utilized the most common type of soft actuator, the fluidic actuator. Many modern fluidic actuators are created from an elastic polymer that includes sections of inelastic fiber reinforcement. When channels of the finished actuator are pressurized, the elastic sections of the actuator expand, while the inelastic sections do not. This relationship between the inextensible and elastic sections of the actuator ultimately characterizes the expected motion profile associated with increased pressure of the actuator. By modifying the geometries of these materials, fluidic actuators may be designed to curl, twist, or bend in numerous arrangements. Specialized elastic polymers may also be used to create motion profiles without the need for external fluid pressure. Shape memory polymers, or SMPs, are often very compliant under normal room temperatures, but when heat or light is applied to the polymer, it will revert to the original geometry it possessed when initially created. Not unlike shape memory polymers, cutting-edge research completed by scientists at Northwestern University demonstrated how a specialized molecular synthesis could be used to actuate a simple soft robot. By reprogramming the molecular structure of a hydrogel matrix to repel water in the presence of light, the four-legged Northwestern robot could be directed to stand up. In addition to the hydrophobic actuation, the Northwestern robot could also be directed to walk forward, utilizing externally applied magnetic fields. Just as important as a means to actuate a soft robotic is a means to determine what the robot is doing. Especially with soft robotic actuators that use light or heat to control the motion of the system, sensory feedback is required to use the actuator with precision. However, traditional hard electronic systems are not immediately compatible with the compliant nature of a soft robot. Scientists are therefore interested in creating sensors and other feedback systems that are as flexible as the material being utilized to create the soft actuators. One such effort published by Kiyoshi and Hirata show how flexible temperature sensors could be integrated into a pneumatically actuated microfinger. The study emphasized the importance of developing sensors that could bend with the compliant member of the finger without compromising the accuracy of the temperature reading. Further research conducted by the Massachusetts Institute of Technology has taken integrated sensors to new heights with prototype piezoresistive skins. With strips of special piezoresistive material applied to the exterior of an elephant trunk-like soft robot, the flexing of the robot could be effectively measured by the resistive change in the material strips. Further study with a neural network allowed the soft robot to learn how to accurately move the trunk actuator with only the piezoelectric sensitive skin as feedback. It is clear that the field of soft robotics will continue to burgeon with cutting-edge technological advancement, and while developing these technologies will take time and great devotion from scientists across the globe, it is also clear that soft robotics has the potential to completely change the architecture of future robotic systems. Indeed, it may be a hard road to perfect such systems, but there's little doubt that the future of robotics will be soft.